Good day, ladies and gentlemen. In this presentation, I'll be looking at cyclones in the iron ore industry, factors that can influence the performance after they have been sized and selected by suppliers. So I will be looking at dense media separation, looking at some examples in that territory, then moving over to a magnetite milling circuit, followed then by conclusions. So on the dense media separation, and you've seen now the presentations earlier today about the history and some background on the iron ore. So iron ore used for the steel industry. Earlier processing was mining, crushing, screening and selling, and direct shipping, or as you've heard as well, is still falling in that category. But there are ore bodies that is becoming more difficult, lower quality ore bodies that needs to be exploited. There's also a stronger environmental focus coming to the foreground, and therefore upgrades are required. So the reason for the processing is to provide obviously a higher Fe content in the feedstock to the steel mills and reduce the impurities like silica, alumina, sulfur and phosphorus. That also results in the reduction in carbon footprint and the emissions, and there's a very strong focus these days coming to the foreground on this specific topic of the reducing the carbon footprint. So processing of iron ore is seen to become more and more relevant in the near future. The objective of the processing, maximize recovery and yield, like in any process, and minimize then the operating cost. In this example, I divided it mainly into a DMS and a hydrocyclone environment, but hematite and magnetite are the two predominant ore bodies that is being focused on over the world. With hematite, coarse and medium sections are normally treated via dense media separation or jigging. So hematite is your dense media separation activity, magnetite the milling and classification activity. The fines and the slimes on the hematite normally treated via spirals, feeder bed separators, wet high intensity magnetic separators, flotation. And then on magnetite milling, hydrocyclones, low intensity magnetic separators and flotation. So I'll look at the hematite environment and the magnetite environment in this presentation. So for those who may not be familiar with dense media separation, what is it? When you start looking at the ore body, there's some properties that you need to determine and see which one can be exploited most economically. And with hematite, density is the property that can be exploited. So when you've got a mixture of ore coming from underground, it consists of valuables and non-valuables. And you need to separate those valuables from non-valuables. And the one way of doing that is to introduce it into a liquid that's got intermediate density between the floats and the sinks. Introduce it into the liquid and leave it over time, and you get then a separation where the light material will float and the heavy material will sink. And this liquid density can then obviously be altered to decide how much of the material needs to float and how much needs to sink. But the picture just shown to you is that's on a laboratory scale. When you go into industrial scale, the plant is a bit more complicated. So you've got your feed preparation section, you've got your separation section, and then your media reticulation system. And that media reticulation system is important because that liquid that was shown in the previous slide in actual operations is ferrosilicon, and it's very expensive and you cannot really afford to lose that. So you must recover it as efficiently as possible. So when we start with dense media, looking at the dense media separation, we start off with cyclone selection. This cyclone selection, and in this presentation, this will be the only slide on cyclone selection. We do training sessions where we go into more detail, but this would be summarizing it. You've got your input values. You've got your process values that you need to process. You look at the yield from the ore body. Look at the mass balance and design parameters. You also need to focus on the constraints: top size, breakaway size, number of cyclones, the spigot requirement. You then decide on what cyclone diameter to select, looking at the cyclone capacity, the spigot capacity, and finally do your selection, looking at the material of construction, We do have a range of material constructions, and you need to then adjust to the circumstances or to the requirement and decide what is going to be the best selection for the client. This is what, in a nutshell, what dense media cyclone selection entails. But if you've done your job correctly, if there's enough information, if the information was accurate, then nothing should really go wrong. The unit should perform adequately. However, sometimes there are other activities or other factors just to keep in consideration. The example on the laboratory scale, where you introduce the material into the liquid, indicated, if you look at the bottom picture, a very clean separation. But the reason why it's a clean separation is because there's no time constraints, and it leads to near perfect separation. So in this graph, you've got on the x-axis the densities, and on the y-axis the fractional percentage of material. And the blue line indicates then the perfect separation. So with enough time, you can separate in between two types of in between a density, or separate at the density to split between a light fraction and a coarse fraction. But when you process material through a dense media cyclone, then you've got time constraints, and there's other factors as well that can reduce the separation efficiency, and I'll touch on it a bit later. Because of these constraints, you don't have a vertical separation line anymore. The lines slope, and because of that slope, you now start to get areas depicted in green and yellow, where material has got the probability of being misplaced. So it's not separated at optimum efficiency. As we reduce the efficiency of separation and operation, these shaded areas increase. More material has now got the probability of being misplaced. So just look at the partition curve, and you will note that the shape of the partition curve is just the opposite from the previous slide. If the partition curve sits in slopes in this direction, where the high density goes to a partition factor of 1, your reference is to the underflow or to the sinks fraction. If it's an opposite mirror image and your partition factor is 1 on the light fraction, then your focus is on the flow section. So in this curve here, the focus is on the sink section. So the partition curve is giving an indication of how efficient is your separation. The partition factor, if you battle maybe to understand it, it is like a probability factor. So what is the probability of a material of a certain density reporting then to the sinks fraction in this example? The efficiency of separation is determined via the actual EP value, and that is then the calculation at the top right-hand side, and that is the slope. The smaller the EP value, the more efficient the separation. So optimal DMS performance is associated with a low EP value of a good separation efficiency. We see that in the handbooks as well. So what is the impact of separation efficiency on an ore body? This is an example where a client asked me to evaluate 2 different types of ore bodies. It's the same mining company, but it had 2 distinct characteristics. One was a low near density characteristic, and the other one a high near density characteristic. Now, near density material is the amount of material that's present around the cut density of the cyclone. So if the cyclone, for argument's sake, is cutting at 3.5, density of 3.5, all the material between 3.4 and 3.6 would be classified as near density material. So low near density material is normally easy separation process. High near density material is a more difficult separation process. So the client asked that I evaluated 2 different efficiencies on this material. And the blue line is the good EP value, the red line is the poorer EP value. On the right-hand graph, the red line, the reason for the red line moving furthermore to the right-hand side is, in this example, the product quality of 65% iron was maintained. Superimposing then the 2 graphs on top of each other, you can see that with the poor efficiency of separation on the low near density material, that's about the material that can get exposed to possible misplacement or poor separation. On the high near density material, there's much more material that can get misplaced or separated less efficiently. Compare that when you had a good separation value on both examples. You can see on the high near density environment, if you had good separation efficiency, the impact would have been quite significant in terms of reducing the amount of material that's got the probability of being misplaced. This points then into a specific situation. If you are processing material that is easy to separate over time, you can get away with a poorer separation efficiency over time. But if you maintain that type of operation when you are treating more difficult to separate material, you're going to have a substantial impact on your bottom line. So the evaluation went further with this client. There's the low near and high near density scenarios, looking at then a low EP and a high EP value. Just a point, this high EP value of 0.067, these are not theoretical values. I will show you later in the presentation how easy it is to get to these values and often exceed it as well. Treating then 1,000 ton an hour, 65% Fe was the aim. You will see that the yields are different because it's different ore bodies, but the difference in treating low near density material versus high near density material, the difference in poor and good separation efficiency can be seen then on the last line. Is low near density material separation ore bodies is not so, it does have economical impact, but not so significant as what you have with the high near dense environment. So there's one area which can become a problem, even though the cyclone has been selected correctly. So coming back to this graph, comment was made, optimal DMS performance is a low EP, is associated with low EP value. That's what the handbook say, that you see in theory, and everyone agrees with that. That is true. What is not always becoming so clear is that you also need to be at the correct cut density. Now, cut density is this 50% point on this curve. That is the density where a particle has got a probability of 50% going either to overflow or to underflow. So that's what we refer to as the cut density. So for some of the viewers, most probably is going to tell me, but how is that possible? Because you've got a SCADA system and you've got a process or density control system built into the system. So how on earth would you go and not operate at the correct cut density? So here's an example of a different plant. The shaded area is where the SCADA set point is. And the two other lines is where the tracer tests indicated the cut densities was. The problem on this side here is, and the client did a thorough investigation, is the media characteristics. This is a settling test, just over time. The red and the green lines are new ferrosilicon, and then the media that's in process. It shows a different type of settling rate. So the media is unstable. So now the question is, where do you need to go and look for the problem? But that is how a cut density can change. So going back to the lower near density material, because that was also an additional evaluation requested by the client, is the cut density has been changed from 3.315 to 3.345, a 0.03 density difference. So it's not a big difference in terms of how much the cut density can drift. On the low and high near density environments, the yield dropped then about just over 2% on the low near density environment, and then about 3% on the high near dense environment. That is the change in quality. On the low near dense environment, 0.25% iron content change, and on the high near dense environment, 0.4% change. On the economical side, that is the impact that you could see on your low near gravity material, obviously about 13 million US dollars, and then on the high near density material about 25. So that is now, if you speak to people, to clients, I would say, but hang on, why is this a big deal? Because the product quality, if it's changing, we will be aware of that, and we will take counter action to make sure that we counter for this deviation. This is a comparison between a laboratory and an online analyzer. I was looking for different data to illustrate the point, but the factor to keep in mind with sampling is variance. Willem alluded to that as well. Now, to use this as an example, the same sample was analyzed by two different methods, and look at the difference in quality results that is being reported. The presentation, the purpose of showing this slide is not to compare these two methods. What I want to illustrate is that there's a variance in your results that you are measuring. And that variance can sometimes not be able to measure a 0.4 density, quality variation. Coming back to this slide here, on the linear dense environment, there was a 0.4 difference in density. Can your system measure that? If not, then you've got a problem and you may be losing money without you knowing it. Having proper sampling systems is a starting point. Willem has spoken about that as well. So in some operations, the sampling is not always done correctly. 80% of your sampling error comes from sampling, from the actual sampling activity. So just keep that in mind, because that will help you to minimize losing money. Another factor, the media. In this example, this is a comparison between an operating density of 3.4 going up to a density of 4. Brent mentioned earlier in this presentation about ultra-high dense media separation that's starting to become more and more popular in the iron ore industry. Now, what this triangle show is a relationship between the percentage of slime, the amount of minus 45 micron, and the sericity of the media. And the operating window on lower operating densities is fairly large, but as you go to higher operating density, you need to be spot on with your media. Now, the sericity is a function of the supplier of the ferrosilicon, but the slimes and the ferrosilicon is a function of the process. Your feed preparation system needs to be up to spec. That's where the screening panels, knowing the screens is coming in, and then you've got the minus 45 micron on the other side. What's happening with you? How do you recover your media? How efficient is your system operating? So there are other, again, the cyclone has been selected, but it's going to get affected if there's not, if the rest of the process is not optimal, and suppliers need to know that. So on DMS factors now, the cut point shift and the EP value that we started to talk about, there's now the factors of media composition, which is creating media stability, which is a function of media stability, media rheology. You got your equipment geometry. That's where we selected the cyclone. Feed characteristics play a role, and then operating conditions. So you've selected the cyclone. Now we're looking at the operating conditions to the cyclone. But then there's a third issue there, operational. Items that could get misaligned, creating then inward steps, creating turbulence. That turbulence is creating misplaced material. So equipment not operating at the correct conditions. These are two speaker discharges from cyclones on the same distributor, coming from the same pump. Something is wrong here, but that operation continued. On the densification circuit, the pipe densifier, the client battled to maintain density. Only later, when we inspected the system, to realize that whoever did the installation, there was an oversight on one of the pipes, but he lost money during that period of time. Coming back to the comment I made earlier, to see a 0.067 EP is not difficult. So these type of conditions create a problem for you, can create a problem in your process, although the cyclone has been selected correctly. So you've got your cyclone selection activity. That's where you get all your information. You need to look at the conditions, the feed conditions to the cyclone, but then you also need to be able to look at the overall process. If you optimize all three areas, that is where we are performing optimally. Moving on to the magnetite circuit, there you use hydrocyclones like the picture on the right hand side. And this is a case study where Multotec was involved with a client. We supplied cyclones. This circuit consists of a primary, secondary and tertiary milling circuit. Primary milling circuit has got screw classifiers. The secondary and tertiary circuits has got then some mill cyclones, closed circuit mill cyclones. And the cyclone overflow will go into a magnetic separator stage, and the magnetic separator concentrate will move on to the next milling stage, and so forth. So the requirement was to treat it just over 400 tons an hour and take up the feed rate of 34.5% to 66%. So that was the brief that was given to us. We worked with the engineering house on this topic, on this project. And after some time, these were the results that was produced. And starting with the bottom, that's the grade. 66% FE could not be achieved at that point in time. And that became a problem because the thinking was, well, how are we going to get to the 66%? The feed rate was still increasing to the 400 mark, and then the minus 71 micron was slowly starting to be increased to improve on liberation. Now that started off when we started to look at the third stage magnetic separator section. What you've got now is the amount of minus 71 micron going to the magnetic separator, and compare that then to the final product being produced by the magnetic separator. And you could see that it does seem that the finer the material becomes, the better the iron ore content should be, which makes sense. It's better liberation. But it does seem that something is, it looks like a wall that sits on this side here. But the focus became the cyclone overflow needs to have a finer fraction, and there was a lot of focus on the cyclone. And we start to look and say, okay, one of the things with hydrocyclones, you need to add water to improve the separation efficiency, make the cut point finer. That's what we did. Add more water in the tertiary milling circuit, and cyclone overflow percent solids came down because we're adding more water, and we could see that the minus 71 content started to increase. But again, up to a point, and then it stops. So it's like a plateau where it then starts to level off. So re-looking at this data, there was something that was starting to become apparent, and that was that the minus 71 micron fraction increased when the feed rate to the plant decreased. Interestingly, there was no reaction on the grade. So this indicated that somewhere there was an energy limitation problem as well. So we went back and we looked again at the data around the mill, and it indicated that you're not really going to see 96%, more than 96% minus 71 micron coming from the mill circuit. So then you're not going to see that in the cyclone overflow either, because the cyclone cannot produce a finer overflow than the mill itself. Following this, we went back to the data and look at the old circuit and compare it to the new circuit. So the old circuit is the white area, yellow is the new circuit. You've got your first section here, your primary stage. Then you've got your secondary cyclones. There's the tertiary cyclones, and then you've got your secondary magseps and tertiary magseps. Now that is just to give you an idea of how this information is laid out. But what was interesting was we picked up that there was a change in grade between the cyclone overflow and the feed to the magnetic separator on the tertiary stage on the old lines. And if you compare that to the new design, that was not so significant. So that prompted the question, why? Also, the other question was, why is the minus 71 micron when it starts to be liberated a bit more? Why is the grade not reacting? When you looked at the concentrate from the magnetic separator, you realize that there's entrapment. So you can have fine material, but the silica is released. It is not. You don't have to grind finer, but there's silica present that can't get out. And then looking then at the process, eventually realize that this process was part of the old design circuit, and that has been omitted from the new design. And these are called deslimers, and that is taking the silica out of the circuit. So there's some lessons to be learned, but the focus moved then from the cyclone as the culprit to later realize there was a different change in the process that resulted in these challenges. The problem was eventually resolved, but again, just illustrating that the cyclone is not always the culprit. So in conclusion, A 610 diameter cyclone, treating 134 tons an hour, 60% yield, $116 per ton. It's now a bit higher, but this is what you can expect to be generated revenue per hour. Just above $9,000. Per annum, about $66 million, or just over R1 billion. It's from a single cyclone, ladies and gentlemen. A 610 diameter cyclone is expected to last under right conditions for about a year. So that's what you can get. What is interesting is the payback of the cyclone is about a year, sometimes just less than an hour, sometimes just less than an hour. When we deal with clients, it will be amazed sometimes how the price of the cyclone becomes the focus point. And what is not, and for sure you can get cheaper equipment. That is almost a given. But look at the amount of money being generated per annum. What also can happen is the amount of losses that you can start to occur if the unit is not operating correctly, because the cheaper suppliers only sell equipment. They do not understand that in a dense media process circuit, there are various flow lines, which in this case is the green is the media, the blue is the water, the red is the dilute media circuit, the black the correct media circuit, and brown is the ore itself. Each one of those flow category lines can impact the cyclone that sits in the middle of the process. And once something goes wrong, you lose big money very quickly. The same goes in terms of the milling circuit as well. The cyclone is sitting in the middle of the process. So it gets influenced, but it also influences other equipment. And we need to be able to assist our clients. So when the client's got a problem with a cyclone, everyone can help him focus on that and trying to solve the problem. But experienced cyclone suppliers are able to show the clients sometimes you need to focus somewhere else. Thank you.